In question 1b, we will be looking at a beam with a uniformly distributed load, which we can see from these lumps and bumps here. And we also have a force acting here, some moment, and then some other force here. In part I, so Q1, B, I, we're being asked to draw a free body diagram and determine the reactions at A. So let's draw that free body diagram, much like we did in the previous question. Let's just draw a very simplified beam like so. Draw our force across, again, like so. And let's go ahead and label everything. So we have a force of 20 kilonewtons acting here. This UDL, or uniformly distributed load, is 6 kilonewtons per meter. We also know that we have a moment acting clockwise at 35 kilonewton meters and some horizontal force of 15 kilonewtons. However, in addition, notice that we have a constraint here. Because we have a beam, we have this, which means that we are going to have some bending force here, some moment, reaction moment, and in addition to that, and in fact we'll do this in red this time, some moment here, let's call that MA, denoting that we are at point A. We also have some vertical, which is acting technically here, but I, again, haven't drawn my diagram big enough, but I have the ability to zoom in. So let's take advantage of that and move MA out of the way a bit more. So we have VA, or our vertical force. We have MA here, and we also have some horizontal reaction as well, given A, that this is a beam, and also that we have this force acting here. So let's come back and label that HA. And there we go. That is our free body diagram for this beam. So much like the previous part, question 1a, we need to assess the X and Y forces. And again, given that we hope that this beam isn't moving, i.e. that this is in equilibrium, that all of these forces are balanced, i.e. they are equal to 0. However, in addition to that, note that we also have these moments which have to also be 0 in order to satisfy the fact that this beam is going to be in equilibrium. So looking at our free body diagram here, we can start to jot down the forces in the X direction, these forces in the Y direction, and then finally our moments. And let's just also denote that these are moments about A. So let's start with the X direction, the horizontal direction. Here we're going to have HA plus 15, which is equal to 0. So through a bit of rearranging, we're going to see that we can get HA straight away. We're going to get HA is equal to negative 15 kilonewtons. So what does that mean for us? Well, it means that our original assumption here was the wrong way around. So what that means is that we're going to have to remove this, and let's relabel it just for our sanity. HA. And because we've swapped this direction, we can also remove this negative. And that makes sense. In order to keep this in static equilibrium, we want to make sure that our horizontal forces are acting in opposition to each other. So HA is equal to 15 kilonewtons. Similarly, for the y direction, let's write down that we have VA acting in opposition to our 20 kilonewton force, and as well our 6 kilonewtons. But given that this is 6 kilonewtons per meter, and we have a 2 plus 3, so in total a 5 meter beam, we need to multiply our 6 by 5 to give us the full load. Again, let's set this equal to 0. And again, through a bit of rearranging, we can see that VA is going to be equal to 20 plus 30, which is equal to a nice round 50 kilonewtons. Perfect. So we have found VA and HA, which leaves us with finding the moments around A. So finally, we have MA here. And then we are going to be multiplying that by, given that 20 is that by 2 meters and is acting in the opposite direction. If we have a look, we have 20 acting downwards. So our moment caused by the 20 kilonewton force is going to be acting in the clockwise direction. So we're going to have negative 20 multiplied by 2. And in addition to that, we're going to have the UDL, the uniformly distributed load, of 30 kilonewtons in total. Again, acting in the opposite direction, because our uniformly distributed load applies that force this way. So let's write UDL there. So that's going to be 6 times 5. And we assume that this acts, if we replace this UDL with a force in the middle, acts halfway along the beam. So given that we have a 5 meter span, our UDL is going to sit at 2.5 meters, so 0.5 meters. So that means that we are going to have to multiply our 6 times 5, our 30 kilonewton force, by 2.5. And then finally, we can't forget our moment at the end of the beam, acting again in opposition to our moment here of 35 kilonewton meters. Wonderful. Okay, and we set that all equal to 0. So all of these, again, are acting in opposition to MA, which has a sneaky little positive. So again, through some simple rearranging, just adding everything to one side, we get that MA is equal to 40 from 2 times 20 plus 30 times 2.5, which is going to be 30, 60, 75, so plus 75 plus 35. So summing that all together, we are going to get a nice round 150 kilonewton meters. And there we go. If we assess whether or not we have answered the question, where we have been asked to draw a free body diagram, which we have done here, although we have added to it over time, and determine the reactions at A, which we have assessed HA, our moment, and our vertical reaction force as such, 15, 50, and 150 accordingly, with units to boot. Fantastic.